Alrighty, hello. There we go. Just checking my levels. Alright. There we go. Let's mute that. Okay, cool. Hey. Say. Hello and good afternoon. Welcome to the Tuesday edition of Chem 305. Where are my notes? There we go. I don't have any pieces of business presets other than check out the daily mixtape. It's pretty metal. I was writing the lecture notes for chapter 4 because I just like to stay ahead of the game, and there's a lot of metals in chapter 4, and so I was listening to metal, and anyways, give Mastodon. There's 4 Mastodon tracks on today's daily mixtape. I'm not a metalhead, admittedly. I'm not a metal aficionado, but I do dearly love me some Mastodon. So even if it's not your preferred genre of music, maybe you might find something there as well. All right, we are in the middle of chapter 3. We should be polishing it off, possibly polishing it off today. We'll see how today's lecture goes. I wanted to take a moment and just say something about the periodic table. So we ended looking at a couple different ways of dividing up the periodic table. 1, metals versus non-metals, and then 2, the different blocks. And actually, it dawned on me as I was writing chapter 4's lecture notes that there's one last kind of way to kind of look at the periodic table that I wanted to give you. So you'll notice that there are... Oops. Actually, let me start here. You'll notice there's this part of the periodic table that kind of dips down, right? That these two kind of stand like up and above things, and then the periodic table takes a dip in that blue region, and then it pops back up. Those 2 regions that I have boxed in salmon are commonly known as main group elements. So when you hear me use the term main group or main group element, I'm talking about all the elements that fall in this region. And then the region that I've boxed in blue are generally referred to as transition metals. Also, there's more metal, i.e. more justification to listen to Mastodon today. Alright, so these are the transition metals as opposed to the main group. And if you're wondering about the F block down there, those are often called the lanthanides or actinides. But we don't spend a ton of time in this class talking about the F block. So main group is S block together with the P block, and then the transition metals are that region that separates the S and Ps from each other. Cool. So I just wanted to kind of briefly go over that. That way, when I refer to the main group or refer to the transition metals, now you'll know. You'll have a framework. You'll know what I'm talking about. Okay. Now, we're ready to dive into some new material. All right, we're still in chapter 3, still talking about the structure of the atom, and as I said, we're getting ready to transition away from the nucleons towards the electrons. We're going to spend more time looking at the electronic structure of the atom. Now, when I say the word atom, you probably the first thing that comes to mind visually is something that's kind of akin to the IAEA logo, right? The International, what does that stand for? The International Atomic Energy Association, right? They kind of have this like old school drawing of an atom. And when I say the word atom, for better or for worse, this is usually what people think of, something like this, where you've got the electron orbiting the nucleus, right? And this nucleus has one proton in it, so this would be hydrogen, one electron orbiting, all right? And this model of the atom that I've drawn, this is known as the Bohr model. This is the Bohr model of the atom, and even though it's not even though this model is not consistent with all of our most recent data, there's some important features in this model that are true of the atom today, which is why I wanted to draw this out for you. All right. Now this is called the Bohr model of the atom. There's several useful things that we can glean from it moving forward. Specifically, you'll notice that the electron's orbiting the nucleus, right? But that there's several different orbits, all right? These orbits are labeled with the variable n. So the first orbit is called n1. The second orbit is called n2. The third orbit is called n3, etc. All right? And that variable n is called the shell, all right? We can talk about the shell of an electron, and when we do, we're talking about n. So we could say the first shell, second shell, third shell, etc. And that is what we're referring to, all right? The shell tells you several different things. It tells you how close the electron is to the nucleus. All right? And it also tells you the energy of the electron. Jen, great question. So it's the way you write it out is you say that n is equal to 1. Totally. So it's not n1, it's n is equal to 1, n is equal to 2, n is equal to 3. So the shell of an electron, the value for n, tells you two things: how close it is to the nucleus, and it tells you the energy of the electron. And it does this let me switch up my colors here. Small values for n, if it's in a lower shell, this means that it is close to the nucleus, and a large n means that it is, small n is close to the nucleus, and plus it's low energy. All right, so your small values for n, the lower shells, closer to the nucleus, lower in energy. Large values for n mean the opposite, right? So the larger it is, the higher in energy the electron is, the larger it is, the farther from the nucleus it is. All right, and you can see that the shells get bigger and bigger as you go, get further and further from the nucleus. That concept holds true even in the more modern understandings, modern theories of atomic structure. All right, so the Bohr model is good because it establishes a framework for us to think about, like, orbit size, farther from the nucleus, closer to the nucleus, and what that means for energy. But the Bohr model of the atom ends up getting replaced, historically speaking, by the quantum mechanical model. So the quantum mechanical model. All right. Now, in the quantum mechanical model, there's a lot of different components to the quantum mechanical model that we don't get into in this course. If any of you end up taking Chem 400, we'll spend a lot of time, either from me or from someone else, we'll spend a lot of time talking about the different aspects of the quantum mechanical model. This text doesn't get into it, so I'm not going to get into it. But one of the biggest differences between the quantum mechanical model and the Bohr model of the atom is this. In the quantum mechanical model of the atom, electrons move in three-dimensional orbitals. All right? They move in three-dimensional orbitals, not two-dimensional orbits. All right? The Bohr model assumed that electrons just move in a circle around the nucleus, when it turns out they move in three dimensions, all three dimensions, all right? And the orbitals are the shapes that they make as they orbit the nucleus. And an electron moves incredibly fast. It's like Sonic the Hedgehog. It's buzzing around like this manic bee. And it moves so fast it creates a blur, and that shape, the shape of that blur that the electron makes moving around the nucleus, are these orbitals, all right? Now, there are 4 different orbital types, all right? In the quantum mechanical model of the atom, there are 4 orbital types, all right? There is the simplest orbital is called an S orbital, and it is spherical in shape. Right, so it is a sphere. Then you have what's known as a p orbital, and a p orbital has 2 lobes. Both of these lobes are three-dimensional. Right, there's different shading on each half. Next, you have what's known as a d orbital. A d orbital kind of looks like, in shape, 2 p orbitals kind of crisscrossed together, and these are all three-dimensional as well. All orbitals are, and the shading on the d orbital looks like so. Here, hang on one second. I gotta pause for 1 sec. Yo, dudes, I need you guys to just because. Go ahead. Sorry, all the conversations. Bye. Alrighty. I apologize for that strange interlude. I am back. One of the weird quirks of lecturing a college class from home that you don't run into when you're in the classroom is when you're in the classroom, never have to leave and pause lecture to ask your family to have conversations elsewhere in the house. Anyways, oh wow. So those are our orbitals S, P, and D. The F orbital shape is super gnarly. So gnarly that I'm not even going to draw it. All right. So there are these 4 orbital types. All right. If you want to see, by the way, a picture of an F orbital, you can Google it. Google image search F orbital, and you'll see why I'm not even attempting to draw them. These are 4 different orbital types, and on each shell, there's different quantities of each orbital. There are, for example, in each shell, 1 s orbital, 3 different p orbitals, 5 different d orbitals, and 7 different f orbitals. In addition, these orbitals have different energy levels. So we know that changing shells can result in different energy levels, right? As you get higher and higher and higher with your value for n. Jen, you feel me? Sorry, I just have to find the perfect emoji. There we go. So you've got these different orbital types. We know changing shells changes the energy of the electron. Changing the orbital type that the electron is in also changes the energy. And if we were to rank these from lowest energy to highest, they would rank like so, where S is the lowest energy orbital, and F is the highest. And let me just make this explicit. Here we're talking about energy. Brianna, great question. Each electron, each orbital can hold a maximum of 2. 2 electrons can fit into each orbital. All right. Now the orbital types that we are talking about right here, we could say orbital types. We could talk about the S, the P, the D, the F, but these are called subshells. All right, so you can talk about the shell of an electron, right? What energy level that it's on, but then you can talk about the subshell, right? We can talk about the P subshell, the D subshell, the F subshell, or the S subshell. All right, so we've got 4 different subshells that can exist theoretically on any given shell. One last thing to be aware of is that every shell, oops, I don't know where I wrote an X. Every shell, with the exception of the first, has multiple subshells. So the Bohr model of the atom is good because it gives us this idea of like you move farther and farther from the nucleus, but really the picture of the electronic structure of the atom is so much more complex. It's not just concentric circles. It's the first subshell, you've got an s orbital. Second subshell, you've got a bigger s orbital and 3 p orbitals. Third subshell, you've got an s orbital, 3 p orbitals, and then 5 d orbitals. It's a very, very vibrant, thrumming, kinetic environment, not just this kind of simple planetary model that we believed for hundreds of years. All right. Now, we are about to start talking. That's kind of our introduction to the quantum mechanical model of the atom. And we're going to use this newfound knowledge to write out something called electron configurations. And orbital diagrams. All right, electron configurations and orbital diagrams. All right, and both of these, both electron configurations and orbital diagrams, are depictions of an atom's electronic structure. They're ways of depicting, of displaying, of showing where the electrons are as they buzz around the nucleus. All right, and something that's going to be useful that we're going to want to keep in mind as we go about writing out our electron configurations and orbital diagrams is the following little graph. This has energy on the y-axis, and on the first shell, so when n equals 1, there is one s orbital present. When n equals 2, on the second shell, there's one s orbital, and you also have a p subshell, and there are 3 p orbitals. When n is equal to 3, on the third shell, there are 3 subshells available. You've got 1s, 3 p orbitals, and 5 d orbitals. And then on the fourth shell, there are 4 subshells available. There's an s orbital, there are 3 p orbitals, 5 d orbitals, and finally there are 7 f orbitals available on the fourth subshell. All right, this is going to be a useful kind of thing to keep in mind as we start writing electron configurations. All right, so we're going to start by discussing electron configurations. Once we have those under our belt, we'll transition over to orbital diagrams. In addition to this nifty little graph, you'll find it useful once we start doing examples, but I just want to lay down the rules for electron configurations, writing electron configurations. First, when we are writing electron configurations, the lowest energy orbital fills first. All right, so when we start placing electrons around the nucleus, the electrons want to get as close to the nucleus as possible, right? Because the negative is attracted to the positive. So they will always fill the lowest energy orbital first because those are the orbitals that are closest to the nucleus. The second rule to keep in mind is something called the Pauli exclusion principle. All right, Pauli exclusion principle is actually the answer to the question Brianna already asked. Pauli exclusion principle states that 2 electrons maximum can occupy an orbital. All right, 2 electrons max. And then third and finally, is something called Hund's rule. And we won't start applying this until we start writing out orbital diagrams. So I'll state it here, but then we'll come back to it. Hund's rule says that electrons only share orbitals when they have to. And we'll talk about what does that mean, when do they have to, when do they have a choice. We'll come back to that a bit later, all right? But these three rules are these three rules and this graph are what we're going to use to now start writing electron configurations. All right, and to do that, let's start with the simplest atom we have available to us, hydrogen. All right, now hydrogen has one electron, and given the choice, that one electron is going to want to get as close to the nucleus as possible. So it's going to occupy the 1s orbital. All right, so this is the electron configuration for hydrogen. I'm actually going to just write that a little cleaner. Let's see. So let's say for the p orbital. Okay, Brianna, you have a question. It only has 3 orbitals. Does that mean yes? Okay, Brianna, great observation. So I started writing at yes. At Brianna. Yes. So Brianna asked. She said, so for the p orbitals, there are 3 orbitals in the p subshell. Does that mean that the p subshell can only hold 6 electrons? And that is exactly what it means, right? 2 electrons per orbital. The p orbitals have 3 orbitals in their subshell, so 3 times 2 is 6. The p orbitals can hold a max of 6. D orbitals, 5, can hold a max of 10. F orbitals, that subshell can hold a max of 14. All right, here's a breakdown of what the electron configuration means. All right, so this right here, this 1, is your value for n. That tells you the shell. All right, the letter here, S, this tells you the subshell. And then this superscript right here, this number 1 tells you the number, I should say, give me a second, I should say the total number of electrons in this subshell. All right, so that is what all the parts of the electron configuration means. You have the shell, the subshell, and then the number of electrons in that subshell. All right, so that is hydrogen. Let's move one over on the periodic table and look at helium. All right, helium has 2 electrons, all right, and they both can fit in the 1s orbital. So for helium, the electron configuration is going to be 1s2. All right, let's take a look at lithium. All right, now for lithium, we know lithium has 3 electrons, right? Our first 2 electrons are going to go into the 1s orbital, all right? But the 1s orbital can only hold 2 electrons, and you'll notice that there are no more orbitals available, no more subshells available on the first shell. So we have to bump up to the second shell, and here we have a choice. Will that 3rd electron go for the s orbital or the p orbital? And the answer is it's going to go for the s orbital, because the electron will always select the lowest energy orbital possible. So it's going to go into the 2s orbital, and we put 1 electron there. All right, so the electron configuration for lithium is going to be 1s2, 2s1. All right? Now, let's do a few more of these. Let's take a look at carbon. All right, carbon. So carbon has 6 total electrons. We're going to put the first 2 into the 1s orbital because it wants the electrons want to go to the lowest energy orbital possible. After that 1s orbital is filled, we're going to fill our 2s orbital, which can hold a maximum of 2 electrons. All right, but the 2s orbital can only hold 2 electrons, so now the next 2, right, we've got 6 total, have to go into the p subshell. So the electron configuration for carbon, 1s2, 2s2, 2p2. All right? Let's jump to oxygen. Oxygen has 8 electrons. We have 8 electrons to house. The first 2 will fill up the 1s subshell. The next 2 will fill up the 2s subshell. So we've housed 4 of our 8 electrons. The remaining 4 will go into the 2p orbital. Now remember, this is totally okay because we have, on the second energy level, 3 p orbitals available, each holding 2 electrons. So the p subshell maxes out at 6 electrons. So 4 in the 2p subshell, totally fine. All right. Now, I'd like to take a look for a moment at, so we'll do one more electron configuration example, and then we'll take a look at orbital diagrams. Let's look at neon. All right, neon has 10 electrons. Our first 2 electrons will be housed in the 1s subshell. Our next 2 will be housed in the 2s subshell. We've housed 4 of our 10 electrons. We've got 6 more to place. And these will fit nicely into the 2p subshell. So that is the electron configuration for neon. All right. Let's take a moment. Let's take a moment to talk about orbital diagrams. All right. Now your orbital diagram comes directly out of your electron configuration. So anytime you want to write your orbital diagram, you do so based off the electron configuration. All right. These two go hand in hand. Now, in an orbital diagram, you represent each orbital as a line. So here, for carbon, you can see that we have, the 1s subshell. So that's represented by a line, 1s. We have the 2s subshell, gets its own line, and then we have the 2p subshell. Now, because there are 3 p orbitals in the 2p subshell, we write out 3 lines, okay? In electron configurations, you only represent the subshell. In the orbital diagram, you represent each subshell, but then you put one individual line for each orbital present in that subshell, all right? And now, the electrons are represented in orbital diagrams. They're represented as lines. So, and actually, I don't want this in yellow. I want it in this kind of warm salmony color. All right, so we have 2 electrons in the 1s orbital. That is represented by an arrow pointing up and a second arrow pointing down. Same with the 2 electrons in the 2s subshell. Now, with the electrons in the 2p subshell, I'm going to show these with green. There are 2 correct ways to depict this, and then there is 2 two incorrect ways. I'm going to just scoot these down. So this is where Hund's rule comes into place. We have two electrons in the 2p subshell, all right? All the orbitals in a subshell have the same energy. So when it comes to placing these two electrons in the p subshell, you need to put them in different orbitals. Because all three of these orbitals have the same energy, the electrons are going to spread out. Remember, electrons are all negatively charged, and like charges repel each other. They do not want to share an orbital unless they have to. The only thing that can cause an electron to share an orbital with another electron is if there's only one orbital available that has the lowest energy possible. But here, since we have three different orbitals, all the same energy, they're going to spread out. Electrons are basically like kids, right? So for example, I have one sister who's 3 years younger than I am, and in the 90s we were living in a 3-bedroom house. My parents had their bedroom, and then I had my room, and my sister had my room, or had her room, right? There were 2 rooms, 2 kids. The 2 kids didn't choose to live in the same room because they'd rather have their own room, right? But then my brother was born, and now I had to share a room with him, all right? And that's kind of how electrons fill orbitals. They spread out, one per room, until you start having to double up, because just because you have another kid doesn't mean you can buy a bigger house. So anyways, that's the kind of way to think about Hund's rule. Electrons are like children. They only share rooms when they have to, all right? Now, this is one correct way to write the orbital diagram for carbon. I'm going to draw a second correct way. So this would also be correct. Is if you had both your 1s and 2s subshells filled, and then you drew your arrows pointing down, all right? Both of these are correct. This is something known as, we'd say that this is spin parallel. All right, that's spin parallel. As long as those 2 unpaired electrons are pointing in the same direction, they can both point up, they can both point down. Perfectly correct. The next 2 things I'm going to draw are incorrect ways of writing the orbital diagram. All right, so if you write it like this, you're wrong. If one's pointing up and one's pointing down, that is incorrect. Or if you write it like so, and then you put them both together, these are both wrong. All right, the reason why they're wrong, well, the second one violates Hund's rule, right? Those electrons don't want to be in the same orbital when they have all of these p orbitals available. The reason why you have to have your spins parallel is the motion of a charged particle through space generates a magnetic field, all right? And we know that magnetic fields, magnets like to line up in a certain way, right? They don't like to be anti, they like to be lined up in parallel. And so that's why those 2, the direction the arrow points, represents the magnetic field generated by the electron, and we know that magnets like to line up, same with the magnetic fields generated by electrons. So as long as they're both pointing up or both pointing down, you're fine. But if they're anti, if one's up, one's down, that is incorrect. That is not a correct way to draw the orbital diagram. All right, now, that was a lot of talking about carbon. The orbital diagrams for oxygen and neon should go a little quicker now that we've had that discussion. So let's draw oxygen's orbital diagrams, or write oxygen's orbital diagram, because oxygen does not have more than one. All right, so oxygen has 2 electrons in its 1s orbital, 2 electrons in its 2s orbital, and 4 electrons in its 2p orbital. So here we're going to fill each orbital with 1 electron, and now we have a 4th electron to place. Somebody's got to double up. It doesn't matter where you put it. You can put it on the right, to the left, or in the middle. They're all the same, but one electron has to share a room. All right, that is the orbital diagram for oxygen. Let's take a look at neons. Two P subshell, 2S subshell, and the 1S subshell. We have 2 electrons, 1, 2, in our 1s subshell, 2 electrons in our 2s subshell, and then 1, 2, 3. I singly filled each orbital. 4, 5, 6. All right. Neon has a full 1s subshell, 2s subshell, and 2p subshell. Everything is filled. All right. Now, at this moment in time, you may be going, okay, Josh, I'm tracking with how to do these so far, but we've only gone up to neon, which has 10 electrons. What happens when we hit, elements like gold that have 79? Like, how do we handle those? This is going to get very long, very quick. And you're not wrong. Fortunately, there's a way to abbreviate or summarize the electron configurations for different elements. And so I'm going to show you with the next example how a faster way to write them, so you don't have to write out everything every time. To illustrate the abbreviation, let's go ahead and write out the electron configuration for sodium. All right, I'm going to move this up a little bit. Now, sodium has 11 electrons, all right? It has electrons, the same number of electrons as neon plus 1, right? So because we already have neon written out here, we know that sodium will have 2 electrons in its 1s subshell, 2 in its 2s subshell, 6 in its 2p subshell, but as we saw in the previous example, our p subshell is full, and so that 1 extra electron has to go up to the 3rd shell, where it has a choice of s, p, and d subshells. And of course, it is going to select the lowest energy orbital, so that 11th electron will go into the 3s orbital. All right, now you can notice something. Notice that sodium has all the electrons that neon has, plus that 1 extra one. All right, it has all the electrons of neon plus that 1 electron in the 3s orbital. It's almost like it has, from an electronic perspective, electron speaking, a whole neon atom plus 1 more buzzing around outside it all. All right, and because of that fact, chemists have developed what's known as the Noble Gas Abbreviation, where we go, okay, we know that sodium has all the electrons of neon plus a little more, so we can write the electron configuration for sodium like this: Na bracket Ne 3s1. All right, that bracket with neon in it means all the electrons of neon plus whatever comes afterwards. All right, we can also, so the electrons on the outside, these have a name. These are called the valence electrons. Valence electrons, they are the electrons. They are electrons with the highest shell. All right. And the valence electrons are the only ones you need to write the orbital diagram. So we can just write this as 3s1. All right. Life becomes a lot simpler once you use the Noble Gas Abbreviation. All right. Now, you may be looking at this and thinking, well, that was easy. That was fine. I could do that, but only because I had neon written out already right next to me. What happens when you ask me for some random thing and like how is this going to be useful in that instance? And I'm so glad you asked, because you have a tool that will make writing electron configurations easy. All right, easy. And that tool is the periodic table. All right, so let's bust ours out. All right, let's take a look at our periodic table. I'm going to scoot it over to the side. Now, the way you can use the periodic table and the Noble Gas Abbreviation to bust out electron configurations like it's your job. All right. This will make writing electron configurations so much faster, so much easier. I highly recommend that you learn this method. All right, this is the Noble Gas Abbreviation. It's called the Noble Gas Abbreviation because group 8, right here, the last group 8A, the last group on the periodic table, these are called the noble gases. And this abbreviation allows us to use only, so that thing that we did with neon or sodium where we said all the electrons of neon, we threw it in a bracket, you can do that for any noble gas, with any noble gas. All right, you're not allowed to put just any atom in a bracket. It has to be a noble gas. You can find those on the very end of the periodic table. You can take a noble gas and say whatever element on the periodic table has all the electrons of this noble gas plus these extra, and then you write out the valence electrons. All right. Now, to use the Noble Gas Abbreviation, you need to keep track of two things. You need to have two things on the forefront of your mind. One, you need to know your blocks. All right. You need to know the blocks we're talking about. And then second, you need to know your periods. Actually, I'm going to change the color. A period to green. There we go. So when I say period, I mean first period, second period, third period, fourth, fifth, sixth, and seventh. All right? All of these periods tell you what shell you're dealing with. All right, so the period on the periodic table corresponds to the shell. You'll see what I mean in a second. Lastly, you need to know your blocks. All right, so this is, just by way of quick reminder, the S block, you have down here, this is the D block. Over here, including the noble gases, this is the P block. And then this, floating down below, is the F block, though we won't really be doing stuff. If you have to take Chem 400, we do get to play in the F block, but for this class, we are staying out of the F block. All right, so remember your periods, remember your blocks. All right. The reason why your blocks are, so the periods tell you the shell, right? So that's why these are important. They give you the shell. The blocks are important because they tell you the subshell of an element's highest energy. Or here, I'll write out energy, I won't be lazy. Electron. The subshell of an atom's highest energy electron is determined by the block that atom falls in. All right? Now, I've written a lot of information on this slide, and you may be feeling overwhelmed. Just hang with me for a hot second. We're going to start doing some examples, and that's going to demystify this process for you. All right? So let's start using the periodic table and what we know about blocks and periods to write the electron configurations for some gnarly atoms. And of course, we're going to start with some simple ones. All right? So let's write the electron configuration for, how about magnesium? Oops. Let's write out the electron configuration for magnesium. All right. Now, first, you got to find magnesium on the periodic table, and then step 2, you got to locate the. So here, let me write these out. Step 1. Find the atom. All right. Step 2. Find the nearest noble gas, and this part's important, with less electrons. All right. The nearest noble gas to magnesium with less electrons is neon. All right. So neon is going to be we're going to use neon as the noble gas abbreviation because magnesium has all the electrons of neon plus a few more. Sorry, I just realized that I wrote this in the wrong layer. Okay. So hang on one second. Oh, there we go. Photoshop wasn't responding, so apologize for the a little bit of a lag there. All right. So neon's our noble gas abbreviation because it's the nearest noble gas with fewer electrons. Step 3. Step 3 is count the periods. Which tells us our shell. All right. And when I say count the periods for magnesium, I mean I need to count down to the place, to the period that magnesium's on. Magnesium is 1, 2, 3 on the third period. All right. And so that's 3, count the period. 4, step number 4 is count through the period, this gives you the electrons. All right, and here's what I mean. So I've counted down, magnesium's on the third period. Now I need to count my way over, and you'll notice that magnesium is 2 spaces in. That means, so I counted down to the period, that we're going to be on the third period. Magnesium is in the S block, and it's 2 spaces in, so that means there are 2 electrons in the 3s subshell, step 4. All right? Let's do another example. Let's do phosphorus. All right? Let's do phosphorus. Let's kind of clear the board a little bit. Yes, totally. Carenza, that's totally what I meant. Is find the atom or the element. Find where the specific element, atom, sits in the periodic table. All right, so step 1, let's find phosphorus. Oops. Phosphorus is number 15. It's right here. Step 2, we need to find our nearest noble gas with fewer electrons, and that will be neon. All right, this gives us our noble gas abbreviation. Now, let's count the period that phosphorus falls on. You can see that it falls right here. 1, 2, 3. And now we have to count our way over to phosphorus. All right, so starting here, we go 1, 2. We go 2 spaces into the 3s block. So this is 3s2. But now you'll notice that we got to jump from the s block to the p block, right? We've filled up our 3s subshell. So now we're talking 3p. And we have to move 1, 2, 3 spaces into the p block to get to phosphorus. So we've got 3 electrons in the 3p subshell, and the electron configuration for phosphorus will be 3s2, 3p4. Cool? All right. Let's do another example. I'm gonna clear some space. Oh, let's see. Could you explain how step 2 again? Confused on how you choose neon. Okay. So at Samantha. Oh, that's me dictating what I'm literally typing. So this is step 2. You always select the nearest noble gas with less electrons. For the abbreviation. Phosphorus has 15 electrons. So neon has 10 electrons. Is the noble gas. We use. All right, Brianna, does that mean that phosphorus has 3 unpaired electrons? Yes. Phosphor. Oh wait, hang on 1 second. Hey, I'm teaching. I just was like, what the heck? Okay. No worries. It's okay. Alrighty. I'm sure you all heard that blast of noise. It's that thing where everybody knows that you shouldn't turn on the TV, but then somebody does. Okay, so Brianna, phosphorus does have 3 unpaired electrons. All right, and okay, working my way down. Yes, totally. And Brianna, you would know that by once you have this, for example, this electron configuration. You write out the orbital diagram, and you put 2 electrons in your 3s orbital, and then 1, 2, 3. There's actually enough room for phosphorus to have 3 unpaired electrons in its p subshell. Okay, proton 3. Yep, totally. Okay, so that's phosphorus. Let's see how we do it on time. Okay, let's do another example. Let me just clear some space. Let's do a few more. Let's take a look at chlorine. All right, so first, step number 1, we got to locate our chlorine atom. Ah, yes, Susan, that is correct. There are 3 2p orbitals before we start filling the 3rd shell. Oh, Jen, I'm so glad. I'm glad it's starting to click. Electron configurations are the type of thing where you write out all the rules, and before you start doing it, it seems really confusing. But then once you start doing it, it has a rhythm and a logic that starts kicking in. So step number 1, we found chlorine. Step number 2, nearest noble gas with fewer electrons. Again, we're dealing in neon. This is not a coincidence. I'm avoiding something on purpose. Let's find the period that chlorine is on. It is down on the 1, 2, 3rd period. So now we have to count our way over. So first we go 1, 2, and now we've completely filled our 3s subshell. Next we're going to jump from the S block to the P block. So now we're filling our 3p subshell. Brianna, you are not you are not alone in thinking this is way cooler than sig figs. Jumping over to the P block, we go 1. Whoops. Let's go 2, 3, 4, and 5. We jump 5 spaces over, so that means we will have 5 electrons in our 3p subshell. If we were to write out the orbital diagram, we have our 3s and our 3p. 2 electrons in our 3s, and then we have 1, 2, 3, 4, 5. 5 electrons in our 3p subshell. And so if they were to ask you in a homework problem, for example, how many unpaired electrons does chlorine have? The answer here would be 5. Cool? All right, we're going to end lecture. Not quite yet. I've got 2 more examples, and then we're going to end on a cliffhanger. All right, so for my next example, I want us to do argon. Let's do the electron configuration for a noble gas. All right, argon is right here, which means its nearest noble gas with fewer electrons is neon. We throw neon in a bracket. Argon is right on the 3rd period. 1, 2, 3. So we know we're going to be filling our 3s subshell with 1, 2 electrons. Then we jump over into the p block. So now we got 3p. Oh, let's see. 5 or 1? 5. Okay. With the previous example, 5 electrons, but only 1 unpaired electron. Chlorine has 1, and this is the key thing, unpaired electron. 5 in the p subshell, but 1 of them is unpaired. Oh, let's see here. We got 2. Okay, just we'll get there, Jen. We will get there. We just have to be patient. Oh, that's why I'm not drawing. Okay, so there's 2, and then argon is 1, 2, 3, 4, 5, 6 spaces in. So argon is 3s2, 3p6. All right? Okay, and again, I'm setting up a mystery. You're going to have to live with the tension, because we're going to ask a question that we won't answer till tomorrow's lecture. But to really draw this out, let's do one more example. Let's do calcium. All right, calcium, we got to locate it. It's right here. Nearest noble gas with fewer electrons is argon. Hey, look at that. We have argon written right there. So we can use it as our noble gas abbreviation. Now calcium is down on the 1, 2, 3, 4th period. It is in the S block. We count over 1, 2 spaces. So calcium has all the electrons of argon, plus it's a 4s2. Okay. Now, this is the electron configuration for calcium. This is the electron configuration for argon. But I want to point something out. Do you remember that little graph that we were using right at the beginning, where we said on the first shell there's 1 s orbital, there's the s subshell. Second shell has 2 subshells, the s subshell and the p subshell. The third shell has 3 subshells, the s, the p, and the d. The fourth has it all. And I'll just write it out for the sake of completeness. Okay, now I want to draw your attention to the third subshell. There's an the third shell. On the third shell, there's an S subshell, a P subshell, and a D. Argon has 0 D electrons, right? You can see it. It only has electrons in the S subshell and the P subshell. So the question is, why does calcium skip the 3D subshell? Calcium has 2 valence electrons, but it put it straight into the 4s subshell with an empty 3D subshell. What the heck, calcium? Now, you may be wondering, did the periodic table lead us to write the wrong electron configuration? The answer is no. This is the electron configuration for calcium. But you're going to have to wait to get an answer to that question. Why does calcium skip the 3D subshell? And do have to worry about this in the future. You're going to have to wait for an answer until tomorrow's lecture. So we're going to put a pin in it here and resume our discussion in Chapter 3. Finish off, actually, Chapter 3 tomorrow with talking about how to handle transition metals and the D block elements with electron configurations. And then we will dive into Chapter 4. So, cliffhanger. This is like the end of Inception, or about as close to the end of Inception as any chemistry lecture can get. What's going to happen? What does it mean? Is that top going to fall? Tune in tomorrow, and we'll find out. Today, if you have further questions, I'm going to ask you to hang on to them, because I've got to run, but I will be back in 30 minutes, and we have 3 hours of office hours. So if you have further questions about other business, hang on to them. I'll come back in, now 25 minutes, and we'll start office hours. We'll answer all your questions, and then some. Cool? All right, dudes, I will see some of you in a bit. The rest of you, I will see tomorrow. Later.